as stated earlier, it's dangerous to subject biological tissue to radioactive substances, particularly radioactive substances that are ionizing, in that they create ionizing radiation like gamma rays or beta particles or electrons themselves, which can cause biological problems. So the way to think about it is complex molecules like DNA and RNA are incredibly long, delicate chains. So if you send a cannonball, or effectively a little, atomic cannonball through that molecule, you can break off bits of that molecule. You can destroy bits of your DNA. And that's what electrons do if electrons crash through at high energy. The way to actually create ionizing radiation is to send in a radioactive X-ray or a gamma ray, have it strike an atom, that X-ray or gamma ray is absorbed, and that electron breaks off the atom and then goes careening through the rest of the cell. It can strike DNA and RNA, breaking those molecules up. Now, DNA is pretty amazing stuff. It can actually repair itself. DNA, if you do have a transcription error or if you have an damage due to ionizing radiation, DNA can actually repair itself unless that repairing structure is what is damaged. Cells damaged beyond repair, and usually you have several a day, cells certainly damaged beyond repair, can do one of three things. The cell can just go into a state of dormancy, where it just doesn't do its job anymore, but it doesn't reproduce anymore either. So the cell is just basically not doing anything. The cell can die. It's programmed cell death, right? Most cells in our body are designed to die after a certain amount of time. Think of the skin cells. The cells in your skin, right, live a certain amount of time, die, shuffle off as we have dust in our house. Mostly it's shed skin cells. But unfortunately, a third thing a cell can do is to go into unregulated cell reproduction. Cells reproduce, and they reproduce usually given a very set stringent criteria. But if that criteria is removed because of cell damage, the cells can reproduce in different ways. For example, maybe the coating that allows the cell to die is damaged. So now you have cells that just won't die. They'll reproduce new cells, and those new cells also won't die. They'll inherit that trait. That is a cancer. Or you can have the cell suddenly start reproducing at a very, very, very rapid rate, much faster than it should reproduce. That is also a cancer. So cancer is just unregulated cell reproduction, in that cells either don't die when they should, or they reproduce at a much faster rate than they should. So cancer is not really a single disease. It's many, many, many different things that can go wrong in the cell replication process. But we blanket term cancer. We use this blanket term to talk about all this type of unregulated cell reproduction. So to measure the damage done and the amount of energy absorbed, because that's really what's happening is when we get bombarded by radioactive ionizing radiation like gamma rays or alpha particles or beta particles, these particles can do damage by basically bringing kinetic energy in and smashing in DNA molecules. So we want to know how much energy does our body absorb from radioactive decay. We get ionizing radiation striking us all the time. Cells die in our body all the time. It's just that our body is designed to be able to repair itself from small amounts of damage. When you get an overwhelming amount of damage, that's when things become grim. So we measure the amount of dose of radiation that is deposited in a body. If 0.01 or a hundredth of a joule is deposited in about a kilogram of biological material, we call that 1 rad. So if you're exposed to 1 rad of radiation, that means that a hundredth of a joule of energy is absorbed into about a kilogram of tissue. And the rad is still used today. Certainly video games and things like that, you might play around with, like Fallout uses this concept of rad, but it's not an SI unit. The SI unit is called the gray. The gray is when 1 joule of energy is absorbed into 1 kilogram of material. So for every gray, there's 100 rads. So this is a way of measuring how much damage does a radioactive source do on a human body or on biological material. Not surprisingly, there's some types of biological material we want to do damage to. For instance, treating cancer. You want to expose it with enough radiation to destroy those cancer cells. Sadly, adjacent non-cancerous cells will also be damaged or destroyed in the process. Or food safety, and we'll talk about that in just a bit. Now, some types of radiation are more effective at destroying DNA or damaging DNA than others. For example, gamma rays, exposed to gamma rays, less likely to do DNA damage compared to alpha particles. So what we need to do is add a scaling factor called the relative biological effectiveness, or RBE. So this is basically a scaling factor placed on all the different types of radiation just to say which one is the most deadly type and which one is the least deadly type. So if you get 100 rads of alpha damage from alpha particles or 100 rads of damage from gamma rays, those two things might not have the same amount of damage biologically to you. So we create a new unit called the Röntgen equivalent band, or REM. 1 REM is equal to the relative biological effectiveness times the amount of rads exposed, the radiation exposure in rads. So this is the non-SI unit. For the SI, we have a unit called the sievert, where 1 sievert is the RBE times 1 gray. So, or I should say, the amount of sieverts, I should say, not 1 sievert, my apologies. The amount of sieverts is equal to the RBE times 1 gray. So, if you're given 1 gray of radiation, 1 joule exposed on you per kilogram, then you can multiply that by the type of radiation, the RBE factor, which is determined by the type of radiation. And here's a scale showing the RBE for the different types of radiation. You can see that the higher the RBE number, the more damaging or deadly that type of radiation compared to those with low RBE numbers. So, and also an equivalent to your book, the dose effectiveness table shown here on the right. So, how do you reduce radiation exposure? We can't eliminate it, right? If you've eaten a banana, you have radioactive potassium in your body right now. If you eat plant life, you have carbon-14 going into your body right now. So you have, or eat animals that eat plants, you have carbon-14 going into your body. So there's constantly some radiation inside and, of course, exposure from outside, from UV light, from the sun, and so on. So the ways to reduce your radiation exposure is to, 1, shield yourself. In space, this is literally, a metal, possibly lead shield that prevents weak particles from getting through, shielding yourself from those rays. If you've ever been to the dentist office or a doctor's office and gotten an x-ray, sometimes they'll make you wear basically a heavy lead shot vest to protect the more vital organs from the x-rays you're getting in your mouth or teeth. For UV radiation, sunscreen protects you, acts as a shield. Additionally, you can increase the distance, right? The further you are away from a radioactive source, the less likely you are to be exposed to that radioactive source. And then finally, decrease the time of exposure, right? If there's a source of radiation nearby, the longer you're near it, the more damage you're going to do. So the only real world example I can think of for decreasing the time of radiation is don't stay out in the sun as long, right? If you're out sun tanning on the beach, the shorter you're out in the sun, the less damage your skin will get from solar radiation. So shield yourself, increase your distance, or decrease the time of the exposure. This is usually all done by dental technicians, right? X-ray technicians. They put you in a room with the x-ray machine, set you up, and then run out of the room to take the x-ray. The reason they do that is while it's okay for the human body, it's acceptable risk for the human body to get a chest x-ray once a year or so, or a few dental x-rays, doing it every single day on dozens of patients, that damage adds up. So dental or x-ray technicians leave the room, right? They increase their distance, sometimes go behind a shielded object to prevent themselves from getting this accumulated damage of radiation in these treatments.